In this video, I told you that we were going to go back and we were going to talk about the alkyl halides. And this is because we left those out of our description so far up to this point, but we are not going to leave them out. We're going to focus on them with this particular video and figure out where they really do fit in this order of command. The reason I did these a little separately is because the OH, we're only comparing OH to something else. The amines, we're only comparing NH2 with something else. The ethers, we're only comparing the oxygen in the middle to something else, right? The problem with alkyl halides is that they work on a different theory, and the reason is because they're just not simple like that. We have F, and we have Cl, and we have Br, and we have I. So all four of these atoms, the most common types of halogens that we see in organic, all four of these, they're different sizes, aren't they? You know, up here at the top, fluorine is a little bitty guy, and then chlorine's a little bit bigger, bromine's even bigger, and iodine is just huge compared to some of the others. So as we go down that column of the periodic table, we go bigger, 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 bigger because our onion layers get bigger, 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 bigger. There's more and more of them. So period number are the number of onion layers that are associated to that atom. So the boiling point for alkyl halides, it's a little bit more complicated just because we're not comparing an alcohol to an alcohol or an amine to an amine. We're comparing now, I know they're all halogens, but we're comparing now fluorine to bromine, which is completely different from each other. So this is the problem in the halogen group. So they do work a little bit different way, but they're still not complicated. We just have to kind of clear it up a little bit. All right. So the common trend here is that as the atom size goes up, the electron cloud, okay, the electron cloud or electron density also goes up. Okay, that makes sense because we're talking about onion layers of the atom. The layers are getting bigger and bigger, and then everything from the outside layer toward the core is the electron cloud. Okay, all of those areas electrons can be in. Well, the larger the electron cloud, the larger the van der Waals forces. There's more things to overlap. There's more things to touch. It is a bigger atom. And I want you to think of this almost like a bigger alkane. As the alkane gets bigger, 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 the boiling point goes up, up, up. And then as the atom here goes bigger, 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 you need to think that the boiling point goes up, up, up. So stronger van der Waals forces are at play. So what this means is that an iodide structure has a higher boiling point than a bromine compound, which has a higher boiling point than a chlorine compound, which has a higher boiling point than a fluorine compound. It has nothing to do with electronegativity here because they are drastically different in size. We kind of saw this before, and we're seeing it happen again. Size trumps in this case, and many other cases too, by the way. In the field of organic, at least. So here are fluorine, chlorine, bromine, and iodine. All right. Now, that is the individual ranking within the halogen group. We still have to fit it in, and this still has to go in to the overall ranking that we can do with the halogens, and we'll see that. And I'll go ahead and give you a hint. The alcohols are greater than the amines, which are going to be greater than the ethers, and then the halides somewhat fall in here, okay? And then the alkanes. The problem is that sometimes the halogens are actually above the ethers, and this always kind of flip-flops around a little bit. But I'll go ahead and put that there in that location, and we'll do a couple of example problems just so that you can become more familiar and more comfortable with the ranking of the boiling points. But that is the initial location that we're going to put them in for now. All right, so there you go. There's the overall ranking of boiling points in reference to the functional groups as well as just the straight true blue alkanes that we might have in organic at this point. All right, so let's take a look at an example problem, and here's one. It says rank the following compounds from the highest boiling point to the lowest boiling point. Okay, so I'm going to rank them from the highest one first. So I'm going to look at these groups, and it looks like what they want me to do here, it looks like alcohol groups, amine groups, and then groups that don't really have anything on them at all. And we've got to figure out which one is going to be the highest. Okay, so here's how we do this. I look at this structure, or these structures, and I'll look at this one first, and I'm going to rank this one as number 1. All right, the reason is because there's an alcohol group there. I know alcohols trump everything. And with those alcohol groups, in this particular case, there's three alcohol groups, each one participating in induced, each one participating in dipole, each one participating in hydrogen bonding. But there's 3. Nothing else beats that out on this chart. So that's going to be my number 1 position, which means that this is going to be my number 2 position, which means that this is going to be my number 3 position. So now I have taken care of all of the alcohols that are top ranked as far as boiling point goes. All right, so now I've got alkanes that have nothing on them at all but carbons and hydrogens, and then I have an amine group. Well, I now know that amines come next. Amines have higher boiling points than alkanes do, and that's because, again, they can participate in hydrogen bonding, dipole, and induced dipole. So there's my number 4. Now I've got these 2 that I need to worry with, and I got to figure out which one has a higher boiling point over the other one. So if I look, I've got 1, 2, 3, 4, 5, 6 carbons, and then here I've got 1, 2, 3, 4, 5, 6 carbons. So they're being pretty good to me. They're keeping it the same magnitude as far as size and structure goes. So to the left, I've got a structure that is straight chained, and to the right, I've got a structure that is branched. Well, my straight chain has more overlap possibilities, so more induced dipole overlap will happen here, and it gets stickier as far as the bonds go between the 2 molecules. And then that means the branched would be number 6. So that is how I solve these types of problems. That's the thinking that I need to go through in order to figure out which one is going to be ranked first. All right, so let's look at another one. Here we go. It says rank the compounds in each set from highest to lowest boiling point. All right, so for part A, they're treating me pretty good. It looks like all of these have a bromine on it. So that's not really what they want me to pay attention to. What they want me to pay attention to here is the number of carbons that I have in the chain. The one to the left looks to be the longest. The one in the center looks to be the shortest, and the one to the right looks to be in the middle. It's like Goldilocks here, right? One's too hot, one's too cold, one's just right. So out of these, the highest boiling point is going to be my largest molecule. So here is rank number 1. This one comes next because that's the next largest, and then the middle one comes last because that's the smallest out of the 3 that they want me to compare. All right, if I look for B, just to make sure they're not playing any kind of major tricks on me, I'm going to count up the total number of carbons for each one of these. All right, so here's 1, 2, 3, 4, 5, 6, 7, and 8. So there's 8 carbons there. Here is 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 here. 1, 2, 3, 4, 5, 6, 7, 8. So 8 there. And then 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 9 of them is going to be there. So out of this ranking, if I have to rank the one with the highest, it's going to be my biggest one first. So there we go. There's number 1. Now these other 3 all have 8. So they want me to look at other things like branching. So this third one is a straight chain. Therefore, it has more chances to overlap, which means more glue to hold it together. So this is going to be spot number 2. Then between the first and the second one, this one's branched, but this one's more branched, isn't it? So this is spot number 3, and this is going to be spot number 4. And there we go. And then finally for C down at the bottom, C is wanting me to relate the different functional groups together. So the first one doesn't have anything. It's an alkane. The second one's an alcohol. The third one's an alkyl halide. And then the fourth one is another alcohol. All right, so I know that my alcohols are going to be the highest. Now, the difference here is that this one's got 1, 2, 3, 4 carbons in total, and this one has 1, 2, 3, 4, 5 carbons in total. So this is going to be rank number 1, and this will be rank number 2. Now I need to compare these two between each other, and I have a halogen, which does provide dipole interaction. So this beats out the alkane that doesn't have anything at all. And that's just due to the dipole interactions that can come around with my chlorine, right? Now, that is the story with boiling points. And hopefully you feel more comfortable with ranking boiling points at this case and why they are ranked the way that they are. Now, I kept telling you, though, that I'm going to quickly and sneakingly bring melting point into the picture. So melting point is the temperature, of course, that something melts. So that goes from a solid to a liquid. All right, so here's the news with melting point. It's the same. If you just learn boiling point, then you know how to rank melting points. How about that? Yeah, like I said, organic doesn't have to be hard. So now, if you go back and you take a look at these questions and they slap melting point in on you, no big deal. You treat it the same way as you just did boiling points. There's only one little weird thing that happens with melting point, and that is this idea that it should be linear, meaning that as you go up in carbon length or bigger molecules, that the melting point should go up accordingly as well. But it actually really doesn't do that. What it does do is something like this. We see slightly elevated boiling or melting points for even number of carbons. If they're odd number of carbons, they are slightly lower than what we would expect. Okay, so for instance, here we have 2 carbons, here we have 4 carbons, and then here is the third one. So normally what we would expect maybe is the third one to be right there. We go up, 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 but we don't. What we see is a little jig-jaggedy thing that begins to happen between the odd and the even number of carbons. So even number of carbons have a higher melting point than the odd number of carbons do. It's just a weird, strange thing that happens. Quite honestly, you'll never get a question about ranking based on that decision alone. If they are going to give you choices, then those choices are still going to play a factor in the trend because it's still trending up. It's just not as high up as what you thought it was going to be. All right, so for instance, if you take a look at this one, all right, this one's going to be carbon number 9. And carbon number 9 has a lower boiling point than carbon number 10. And then carbon number 10 actually has a somewhat higher than carbon number 11. So there's a little blip into this whole kind of scenario trend relationship. Well, the issue here is that they aren't that tricky. If they're going to give you these to compare, they're going to give you maybe a 10 carbon and a 12 carbon and a 14 carbon. They're not going to make you compare odds and evens between each other because things get so tricky when you begin to do that. So melting points, just keep in mind, it's the same trend as boiling point. If you know what the melting or boiling point trend is, you should never get a melting point question incorrect. All right. Just to prove that point, I'm going to go back to some of these older charts that I showed you. And then here was the one with octane. Notice it also has a melting point here. Well, if I look at the melting point, this melting point, negative 57, negative 121, and negative 107. So the longer, straighter chain has the higher melting point. Even though it's still negative, it's the higher melting point. And as we branch, that melting point goes lower, doesn't it? Well, sometimes we'll find a little blip, And that's okay, not a big deal there at all. But these are just overall trends. That's all that we're talking about. Here's another melting point table that we saw a couple of videos back. Methane, pentane, decane, pentadecane, icosane. And if you look at your melting point, negative 182, we go bigger, melting point goes up. 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 So very similar to the boiling points. There's hardly any difference in those at all. All right, so now we've taken care of melting point. We've also taken care of boiling point. And now we're going to focus our attention to what we call solubility or miscibility. So what are those? What do they mean? How do they play a role in organic? That's what we'll learn about when we come back in the next video.